Good afternoon. Welcome back to the last afternoon of the event. And I have the honor to introduce Roberto Miatello from Cordoba, Argentina. Let me make this clear. And the title of his talk is on the Hodge spectra of length spaces.
Hello. Yeah. Good afternoon. First of all, I want to thank the organizers, especially Claudio and Paolo, for inviting me to talk in this beautiful place and giving a lecture at this meeting. Here. Okay, here. Okay. So the subject of the talk is the Hodge spectra of the length spaces. So that what we shall do is to show how to compute the P spectrum of a length space by reducing the computation to a combinatorial problem. So this was motivated by a question in spectral geometry by several people. So first I will discuss some of the history involving the question of can you hear the shape of a drum. So this is an old question, Mark Katz. Then immediately many examples appeared. The first one was by Milnor, who by means of Witt lattices that were already known, he showed that there are two 16-dimensional tori via the lattices by Witt that are not conjugate in O16, but they have the same theta function. So as a consequence, these two lattices have the same number of elements of each fixed length in R16. So after that, a different kind of example was given by Vignera, Marie-France Vignera, by means of hyperbolic 2 and 3 manifolds. She used quaternion algebras and she used the Selbert trace formula to prove isospectrality. Then many more problems came up. Aikida and others with some length spaces or some spherical space forms, until Toshi Tsunada gave a general method to construct examples. So he took a finite subgroup of the isometric group and two subgroups, G1, G2 of G, that are quasi-conjugate in G, but not conjugate, and acting freely on N. Then he proved that the quotients are isospectral on functions and actually on P-forms and all natural elliptic operators. So after this example came, then the interest... Yes?
Could you give the definition, please, of quasi-conjugate?
Oh, quasi-conjugate means that there is a bijection between the elements of the group that respects G conjugacy. So phi from G1 to G2, such as that if X and Y are X1 and X2 are conjugate in G1, then 5X1 and 5X2 are G conjugate. So there are many examples of that, of finite groups satisfying that, and some of those came from number theory. Okay. So now we look at non-Tsunada isospectral pairs. So that means isospectral pairs that are not isospectral on every operator. So for instance, Carlin Gordon and collaborators, Dennis DeTark, George Wilson, Ruth Gornet, Dorothy Schuth, they gave a large number of examples using nil manifolds. For instance, manifolds that are isospectral on functions but not on one forms. So this is, and then also myself and Juan Pablo Rossetti, and also with Podesta, we gave a number of examples. For instance, manifolds that are p isospectral on p forms for 1p, but not on functions. That's one example. Another type is that are isospectral on functions, but they have different Betti numbers, all different Betti numbers from 1 to n minus 1. So this, if they have different Betti numbers, they cannot be p isospectral. Okay. Then finally, well, Gordon Webb Wolpert proved that you cannot hear the shape of a drum, but still their domains don't have smooth boundary. So the problem with smooth boundary, the original problem of Marquardt, is still open. So as you see, there are two types of the problems of manifolds with boundary or without boundary. So I'm talking about both together. So the question that will be the subject of this talk is a question by Joe Wolf, Carlin Gordon, Peter Doyle, that whether you could have pairs M and M prime isospectral on functions and on p forms for all p, but however would not be Tsunada isospectral. Okay. So this is so the answer is yes. We constructed length spaces that have that property. So pairs of length spaces and that are p isospectral on forms for all p, but still they are not isospectral on certain bundles. Okay? So I will explain the construction, and by means of this combinatorial connection, and then give some open problems on this. Okay, so we start. So we have a length space. So we have the 2m minus 1 sphere. So we take Z1, Zm in Cm, complex numbers, so such that this sum is 1. So this is the 2m minus 1 sphere. We take a natural number and this finite cyclic group generated by gamma, and the action is given as follows. We multiply each coordinate of Cm by this root of unity, and we assume that the Sj's are co-prime to Q. Okay, this is a cyclic group of order Q, co-prime to Q, so that the action is free, and the quotient will then be a manifold, and its length space with parameters Q, S1, Sm. We write the quotient as the sphere as a quotient of G and K with these two SOs groups, and then we will use representation theory to determine the spectra. So the L2G mod K, so this is the sphere in this case, is a sum of representations where G acts by translation on the left by x minus 1 of all representations V pi that contain the trivial representation of K. So this is Frobenius reciprocity. And more generally, if we take any representation of K, unitary representation of K, everything is finite dimensional here. So we take L2GK tau, which is essentially this, is the set of functions from G to vector value to V tau, such that FGK is tau K minus 1 f of G, plus a condition of norm 2 being finite. So this also is a representation of G that looks like that. So the V pi's occurring are those such that the pi restricted to K contains the dual representation of tau. So this is Frobenius reciprocity. We can also look at this representation by taking a homogeneous vector bundle, E tau, defined like this over G mod K, and let G act on L2 sections. Okay, so now we are interested in the sphere case, and tau will be tau P, the exterior representation of this space of SO2m minus 1 on lambda P of Rn complexified. So the Hodge Laplacian is given essentially by the action of the Casimir element, that is a central element in the universal enveloping algebra of the Lie algebra. And the Casimir element acts by scalar, we call lambda pi, on each irreducible representation pi. So the scalar looks like that. This is an inner product, and this is the row of Lie theory. So it's 1/2 the sum of the positive roots. Lambda pi here is the highest weight of pi, which will determine pi completely. So now, in order to compute the spectrum, so we need to compute these numbers, and then we need these representations. So that these representations are those representations contributing to the spectra. So those occurring in L2, in this space. So those, they have a highest weight that looks like this. This is a basis. You can think of it as the canonical basis in the Lie algebra of the torus. So this, if P is 0, then we just have the trivial representation. So all representations that contain the trivial representation of K have this type of highest weight and are called these spherical harmonics. And this is a sort of a generalization of the spherical harmonics. So now the thing looks like this. We have L2 of the sphere, tau P, and then the eigenspace with the eigenvalue lambda can be described as a sum of V pi's, where the pi's have to be in the right space, and the eigenvalue lambda pi has to be equal to lambda. Well, this I already mentioned. So this. So now the eigenvalues of the P Laplacian or the Hodge Laplacian, P Hodge Laplacian in the sphere, they are well known. They are a bunch of, is a union, disjoint union of two sets that look like that. This is classical. The eigenvalues of the length spaces will be a subset of this, because we are taking a quotient. So this is like two strings. You see they are, the string is, if you take k equal 1, 2, and so they are infinite strings. and they are disjoint. This, if you put P plus 1 or P, then you get disjoint sets. So now for the length space, we need to take gamma invariants. Now the gamma invariants involve taking gamma invariants in the V-pies. So now we have to do a little calculation. So we take the maximal torus of SO2M. It looks like matrices of this type. The block matrices with... this is a maximal torus, is contained in G. And then we have the characters, mu. And then the action looks like that. If we take one element like that, H to the mu, and mu looks like that, then the action is just, the character is just E2 to pi I, some Cj, Tj, where Tj are these numbers. So now we take V pi and we split into weight spaces the V pi. In each weight space, pi h of V is just multiplication by the character. So h to the mu in each weight space. So we have to, in this case, the Tj's look like this. So when we compute gamma V, then we'll get this. And then if we want this to be an invariant, this has to be equal V. So this has to be the sum of Cj, Sj. Sj give the parameters of the length spaces. The Cj's must satisfy this condition. So then we define this. We observe that this is a lattice. This is a lattice in the set of weights, but this is like saying z to the m. These are integers, and this is z to the m. And we take the elements such that this condition is, so the sum Cj Sj is congruent to 0 mod q. So this is a congruence lattice attached to the length space. So the idea will be to translate the P spectra condition into a condition on the length space, on the congruence lattice. So now we reach to this point. We have, for any eigenvalue, then the dimension of the eigenvalue now looks like that. It's the sum of the dimensions over the weights such are in the congruence lattice attached to the length space. So this is where L appears. So the L plays a main role in the P spectrum. So now we will need these counting functions. We consider in the congruence lattice, or in ZM, norm 1. So that means we take the one norm in Rn. So it's just adding the absolute values, okay, the one norm. So we take the counting function of all those elements in L that have one norm equal to k, and then we also define this other counting function that those elements that have one norm equal to k, and the number of zeros is L, a fixed L. So this means we are taking the ball of length k in Rn, so it's a polyhedron, okay, and then this measures also the number. We are counting elements of norm k, but which are on hyperplanes, okay, on one of the hyperplanes. So they have to have the number of zeros. This is the number of zeros, is L, okay. So it's two different. So So now we will need two lemmas on weight multiplicities. And these are important in the sense that we take a weight mu, and then the multiplicity of a weight mu in a representation with this highest weight is combinatorially given like that. And this happens if the norm 1 of mu is given by this number. On the other hand, the multiplicity of, in this second case, is given by this number if the norm 1 is p minus 2r and the CJs are less than or equal 1. This is important because it tells us that the multiplicities are connected to the norm 1s, to the 1 norms of the mu. So now the second lemma, it tells us the following, that we would take this representation, and if you have two weights, because the weights, the multiplicities of the weights of these representations are those that determine the spectra, the p spectra. So if we take two weights with the same 1 norm and the same number of zeros, then the multiplicities are the same. So this is a peculiarity of this type of representations. It doesn't happen for every representation. And it's a key point in the spectrum computation. So now we can compute, let's look at this one only. We can compute the multiplicity of this eigenvalue in very explicit terms, in terms of the counting functions. You see, this is the case of the spectrum on functions. The multiplicity of this eigenvalue is given by this expression. So this tells us that the spectrum is determined by the counting functions of elements of 1 norm equal or with a given 1 norm in the associate lattice, and the p spectrum in a more involved way, involving not only the length but also the number of zeros, so the number of elements in the hyperplanes. So as a consequence, we get that two length spaces are isospectral if and only if the associated congruence lattice are norm 1 isospectral. And they will be isospectral for every p if and only if L and L prime are norm 1 length isospectral. That means that norm 1 star means that they have the same number of elements of a fixed length and also the same number of elements with a fixed number of zeros. Let's look at the classical fact on length spaces now. So this is very classical. Two length spaces are isometric if and only if they are homeomorphic. And this happens if and only if the parameters are connected as follows. There is a permutation and some change of signs, and T in Z, in this case will be, we are taking LQS prime. TQ, these have to be co-prime. And so the S primes are obtained by a permutation of the S followed by a change of sign and multiplied, all of them multiplied by a fixed T mod Q. So this is a classical fact which tells us when two length spaces will be isometric. But then we have to rephrase the third condition. And it's a rephrasing that it's illuminating, I think. This condition can be expressed as follows. there is a z-linear norm 1 isometry that takes one lattice to the other. If you observe, the multiplication by t preserves any lattice, because the congruence lattice is something equal to 0. You multiply by t all coordinates, you will still hold. And then you have permutation and change of sign is a norm 1 isometry. So this says that this tells us when. So our condition gives a relation, similar relation, in a sense that we have to have a norm 1 isometry, but now it need not be z-linear. It need not be linear. It will be a norm 1 isometry such that the number of elements of a certain fixed length will be the same for both lattices. So this resembles like the classical case of the tori, for instance, right? When you don't have, you may have two lattices that are not conjugate, but they are quasi-conjugate in the sense that for a fixed length there is the same number of elements. So let's just see an example. So here is Aikida's all examples. These are isospectral, zero isospectral functions. So this is for m equal length spaces of dimension 5, and so m is 3, n is 5. So the associated lattices, if these are isospectral, this might be norm 1 isospectral, right? But let us see that they are not norm 1 star isospectral. Okay? So let's look at length 3. So for L, you see we need to have that 1 times C1 plus 2 times C2 plus 3 times C3 equals congruent to 0 mod 11. So 2 minus 1 does that. Plus minus 2 minus 1 does that. And this one also does that. Yeah, this has is in this lattice and has length 3. And here we have similarly for L prime, okay? But we see, so the number of elements of length 3 in both lattices is 4. But in one of them, the one with zeros, okay, if you take, is 4. But then the number, if we take this finer measure, that it measures not only the length but also the number of zeros, then the number of coordinates equal to 0, you get different. So they cannot be p isospectral for all p. Actually, they are not 1 and 2 and 3 isospectral. So this is the simplest. Actually, Aikida never gave any examples. So these are the first examples that are p isospectral for all p. So here are they. So this is. So these are the parameters for dimension 3. Dimension 3. So these are isospectral pairs for all p. So these are the parameters, and the parameters are a little bit bizarre in a sense. So these parameters give. So that means that you see this is 7 square, 8 square, 2 times 7 square, 10 square, 11 square. So these are the smallest parameters. But now you see this is for m equal 3. For m equal 4, these are the first ones that the computer will give. Actually, we we cannot be certain that. So at the beginning, we needed a way to count a finite number of eigenvalues and to be sure that these are actually isospectra for all p for any eigenvalue. But this cannot be done computationally but we proved first that it was sufficient to get to a certain number of eigenvalues to be the same so that they will all be the same. So finite condition. We reduce to a finite condition. And now the other thing is that if we look at the examples in dimension 3 and the examples in dimension 4, it's not clear how to go from one to the next one. So this is one of the things that we don't know how to do. I mean, it would be nice to be able to construct examples once you have them in dimension m, to have them in dimension m+1. Okay? But, I mean, this is the first one. And it's not clear at all how to get these from these. Okay? Actually, we don't have. So after these, we got an infinite family. Of course, you want an infinite family. This should be non-zero. If r is greater than or equal to 7 and r is not congruent to 0 mod 3 and t is in n, these lattices with plus and minus are norm 1 star isospectral. So it means that the associated length spaces are p isospectral for all p. So this took us a long time because the first proof was piecing together linear maps given by sectors that respect the one norm. But it's delicate. And then we found a way by using certain generating series, improving they are the same for both lattices. So, as a corollary, there are pairs of non-isomorphic length spaces for any dimension, arbitrarily high, that are p isospectral for all p. But this is not for all dimensions, but for any arbitrarily high dimension. Okay, we could not, but still, if by taking products with spheres, we can get pairs for non-isometric n manifolds that are p isospectral for all p. So the easiest example from our family is this, and now we have to observe that this length space is equal this. We have to multiply by 6 here, and then 6 times 8 is minus 1. Minus 1 is 1. And then similarly here, 6 times 22 and is congruent to 15. So, and this is the same. So then we get our simplest example. Now, the observation is that these examples will not be tau isospectral for other taus. Actually, for most other taus, they will not be isospectral for other representations. So if we take other vector bundles with respect to the canonical Laplacian on the bundle, then if we take these, then we can take a highest weight here, and we have to check the weights, okay, and then the gamma invariants are given by that. And if we take this eigenvalue for this representation, the eigenvalue is 47. And this is the only representation that has such eigenvalue. And then one checks that if we choose tau with this highest weight, satisfying this condition, then the dimensions of the the multiplicities of the eigenvalue 47 in both is different. So they are not tau isospectral. So what that means is that then there are continuations of this. Emilio Lauret, not this one, Young Lauret, and Sebastian Bolt constructed examples that furthermore are Dirac isospectral. And Peter Doyle gave a reinterpretation. And now I give some questions. So first question is to give ways to construct so that these are norm 1 star isospectral in all dimensions. We only did it for dimension 3 and 4, okay? And then with help of the computer you can get more, but you cannot get arbitrarily far. But they should exist in all dimensions. The other question is whether there are families with more than 2 elements. Okay? We only found pairs, but not large families of these. And then the other question is find topological characterizations. So how all these manifolds are homotopically equivalent and not homeomorphic. It would be nice to have a procedure to go from one dimension to the next, and then we could prove this. And then there are connections with toric geometry, because actually we are reducing the computation of the spectrum to counting the number of points in a polytope and letting the polytope grow. So then this is reduced to, this was observed by 2 mathematicians from Iran who sort of translated this by using, there is a paper, I think in Conrandu, they reduced this to toric geometry. But then only the isospectrality question is reduced to toric geometry. So you have to look at bundles over, you have a polytope, and then that gives you a toric variety, and you have bundles, and then you look at sections of bundles and dimensions of sections of bundles, and if the dimensions are the same, so those dimensions determine the spectrum of the Laplacian on the P Laplacian on the length spaces. There has to be a way to go back and forth. Okay? So thanks for your attention.